turned up. Last lecture that you missed was absolutely fantastic, and that was all about OFDM, which was transmitting signals, really, really slow ones, none of this fast pulse business that only causes problems, and using electronics to sort them all out at the end. This one is about how to use a bit of electro-optics and a bit of cheap electronics to mitigate nonlinearity. And the important thing here is I can mitigate cross-phase modulation, which everybody calls the nonlinear Shannon limit. So we've overcome the nonlinear Shannon limit, which means we can increase the spectral efficiency or the communications capacity of an optical fiber using only cheap techniques. So, yeah, this type of dog is called a cur. It's a mountain cur. And the Scottish tend to call dogs curs as well, or other people curs. And what I'm trying to say with this is people get all sort of confused. Maybe not you people, because you know it's your life. Non-linearity is your life. But the self-phase modulation, cross-phase modulation, and four-way mixing. And I submitted a paper once saying you can get rid of four-way mixing by applying a time-dependent phase shift. And the people, they were obviously very eminent people, said, no, this is totally untrue, because four-way mixing is a frequency domain effect, and self-phase modulation is a time domain effect. So how can you undo a frequency domain effect with a time domain solution? There's this thing called Fourier transforms, which link time and frequency domain, probably all sorts of other mathematics as well. So what I'm trying to say is, essentially in an optical fiber, the phase is changed by the near instantaneous intensity. And so there's this thing called a Kerr effect, and if you look at it in different directions, and I'm on video so I have to be polite about this, then it exhibits different phenomena. And for example, if you look at this dog from underneath, you would see four paws, like that. And so obviously that's four-way mixing. If you look at two dogs running past each other in the park, then there will be small interaction as they pass each other involving a bark and a bite. And so the phase of dog one, or the intensity of dog one, will affect the phase of dog two. As it gets bitten, it will slow down slightly, for example. And so that's obviously cross-phase modulation. And self-phase modulation is dogs, that's what dogs do because they can. Right, so in an OFDM channel, we have lots of subcarriers, which are slow. And the initial criticism of OFDM was, it'll never work because pairs of these subcarriers will mix together and produce four-way mixing products. And the number of four-way mixing products you get is roughly proportional to n cubed. So if you have 1,000 subcarriers, you'll get 1 billion four-way mixing products. And how can that possibly work? So for example, these subcarriers here will produce lots of little four-way mixing products, some of which will fall on neighboring subcarriers, and others which will fall out of band. But there's a lot of them. So what might they do? Well, when you detect this signal, you mix the optical carrier with each of the subcarriers by basically doing the modulus squared operation in the photodiode. And you have a vector going to this cluster, and as I said in the previous lecture, that probably represents a data bit, or two data bits, like 0, 0, 1, 1 will be over here, 0, 1 here, and 1, 0 here. And you don't want that vector to sort of come down to here across the axis, otherwise you'll get an error. These little four-way mixing products act like a random walk. They're all random phases because the things that generated them are fairly random phases. And so the result you get is a bivariate Gaussian splodge, for a better word, and you can work out the error rate from the length of these vectors and the number of them. And that produced a nice four-way mixing theory. However, before we came up with a theory, we came up with a simulation, because it's far easier. And this is a sort of graph that's become quite popular, that it's saying that it's a bit the wrong way around, cause and effect. But what we're trying to plot is, as you increase the system length, you get constraints on the optical power. There's a lower constraint here which says, down here, the system is too noisy. So ASE noise from the amplifiers will kill it, and you will get a higher error rate. Above, this is where I need to stick again. Above, at high powers, you've got a constraint due to non-linearity. Due to four-way mixing, or really the Kerr effect. And depending on the number of channels, so if it's sent one channel, one wavelength channel, that's lots of subcarriers, I get a limit like this, and the more channels I have, cross-phase modulation comes in, which limits the power level. And in the middle, you get good quality data. The more in the middle you are, the better it is. If you come down to this edge, then it's noisy. If you go up to the top, it's noisy, sort of noisy, due to non-linearity. Non-linearity doesn't really cause noise, it's deterministic, so we ought to be able to undo it. And what this says is when these two curves come together at, say, 4,000 kilometers, you're trapped between a rock and a hard place, noise and non-linearity, and that's the maximum system transmission distance. Any questions on that? So the idea is you can reduce this by having more amplifiers or having Raman amplification, which would mean the intersect between the top and the bottom would go out and you get a longer system. So having continuous amplification along the system might work. Or you would like to push this up, the non-linear limit, and so the intersect comes out and you can get longer systems. We actually did develop an analytical equation, which I'm quite proud of because it's so simple. Basically, it's saying that Q, which is the quality of the electrical signal to noise ratio of the system, is just 1 over the nonlinear coefficient, the effective length, which is about 22 kilometers for normal fiber, and the power of all subcarriers, all squared. And this works for longer and longer systems. You can get a good fit of the equation and the simulation. So we can predict when the system falls over. And it wasn't a bad prediction. It showed that OFDM could go a few thousand kilometers. And most people thought it wouldn't go anywhere near that. So, what helps us here? Well, dispersion always helps mitigate nonlinearity due to an effect called walk-off. With this diagram, I'm going to explain really my metrics for measuring walk-off. It works quite well with OFDM, but it works equally well with QPSK. It's a bit more difficult to think about. But you can think of any signal as having a lot of tones in it. OFDM, they have fairly discrete tones. Each one's actually a single function, but I've represented them by delta functions. So if we take two tones that are delta little f apart, what they will do is they beat together. So two tones causes a beat. That beat in intensity by the Kerr effect causes a phase modulation. And so if you have another tone anywhere else, then it will be phase modulated, which causes it to have sidebands, modulated carrier, it gets sidebands. That's the communications thing. However, walk-off or dispersion will cause the addition of this effect along the length either to add all in phase, which is very bad, or to sometimes cancel out, which is good. And this is another diagram I'm quite proud of. This is showing the effect of dispersion on four-wave mixing. What I've done is, here is a single length of fiber. It's an amplifier with a fiber afterwards. And the power in the fiber goes down along its length because of attenuation. So the Kerr effect, which is proportional to intensity, is strongest in the first bit of the fiber. If I divide this fiber up into short lengths and try and calculate how much nonlinearity or what these sidebands are, so I've got my sidebands being created, how big they are as I go from section to section, I plot this graph here. So the blue line that you can hardly see is saying in the first bit of the fiber after the amplifier, we've got a strong tone created, it's long. In the next bit of the fiber, the power's decreased, so there's a shorter four-way mixing product or cross-phase modulation product. Doesn't matter which. And then it gets shorter and shorter, and the last 40 kilometers of the fiber doesn't really make much difference. Now, if you have dispersion, then each of the four-way mixing products, as it goes along the fiber, changes phase due to dispersion. And so they no longer add in a scalar fashion. So the first one goes to here, the second one goes to here, the third one goes to there. If I have more and more dispersion, or actually I have more and more frequency separation between the tones, then the amount of phase change per unit length goes up and up and up. And you get these sort of fronds that curl in on each other, rather pretty. So it's like spring. There's certain ferns that sort of unfold themselves in the spring, point towards the sky. So dispersion actually causes the resultant, which is from the origin to the final point, to be smaller. Here was a big, strong four-wave mixing product. Here was less, and here it's a very weak four-wave mixing product. But there's more. If you then put another amplifier after the first span of fiber and start again, then you start drawing a new frond. And the interesting thing is that the new frond carries on from the phase of the old frond. And we'll draw like that, and then the new one starts like that, and you get this sort of effect, which could be in colour, but it isn't. So we start off from the origin. The first frond, the first span of fiber, gets us to there. The second one goes around here and gets us to there. The third one gets us back to near the origin. So 3 spans of fiber have cancelled out four-way mixing or cross-phase modulation at this particular frequency. And we get this graph called the four-way mixing or cross-phase modulation efficiency graph, which says that the strength depends on the frequency separation between the 2 tones and the one that's being modulated and the 2 tones themselves. And where we get a null is where these individual spans of fiber have all added up to get back to the origin. If you have dispersion compensation fiber, it's bad, because each frond starts going upwards, and you get a sort of n-squared effect of four-way mixing. The four-way mixing depends on the number of spans squared, because you've taken out the phase change from span to span with the dispersion compensated fiber. With no DCF, people call this greenfield, throw away dispersion compensated fiber, the four-way mixing efficiency drops rapidly, and this is about 1%, very quickly at high frequencies. And so that's why people want to get rid of dispersion compensating fiber. Any questions? So this is what inspires the next work. This is a bit of a result of system calculation. When we did OFDM originally, the signal bandwidth was about 5 gigahertz, and so there was no improvement due to walk-off. This graph is improvement due to walk-off, which is dispersion, versus the bandwidth of the signal we're transmitting. As we go to higher and higher data rates, you can see that my equation, that simple equation I was proud of, actually underestimates systems performance quite significantly. So magically, if you go at 100 gigabits per second, so about this simple rate, you get improvements of, depending on the link length, 10 or 12 dB, which is significant. So fiber dispersion is really good for high data rate systems because of the walk-off. So how do we compensate nonlinearity? This is the equation for Kerr effect, and there's a warning here that electrical engineers try and make phase a phase advance. Some of them do anyway. And in Agrawal's book, that is always quoted on this nonlinear fiber optics, it's a retardation. So sometimes you see this equation with a minus sign in it, depending on where it comes from. Basically, it's saying the phase shift across the length of fiber is proportional to the power, the number of spans I have in my link, so number of amplified spans, the effective length of the fiber, which is less than the actual length of the fiber because of the attenuation, that's around 20 kilometers, 22 kilometers of single mode fiber, and then the nonlinearity coefficient gamma, which depends on various bits and pieces. So if we apply an inverse phase shift at the end of the fiber or at the beginning of the fiber, just do this but with a negative sign, then we can compensate nonlinearity. How do we do that? Well, in OFDM we can do it quite nicely because we do it in our digital computation just after the inverse Fourier transform. We've got a time domain waveform. We just apply a complex multiplication which applies that phase shift. And the little crosses are without the pre-compensation. Some of the crosses have crossed the threshold, and a 0-1 has become a 1-1, for example. Bad. If you turn the compensator on, just click software, change, then the clusters become tight, and the error rate goes down significantly. And we can actually increase this thing called Q quality factor by 7 dB. What that means in reality is we could double the data rate, double the capacity of the link, just by calculating that equation. Any questions? Is that surprising or obvious?
What are the axes of this diagram which you're displaying?
Oh, okay. So this is a constellation diagram, and it's basically saying there's a real axis, it's an Argand diagram, and an imaginary axis. Communications engineers call this in phase with the carrier, or quadrature, 90 degrees out of phase with the carrier. And that's what QAM modulation is. It's quadrature amplitude modulation, which means you can actually send data on the sine part of the waveform or the cosine part of the waveform. And that means you can sort of double the amount of information. So rather than just sending a real signal that's either here, negative or positive, you can send a signal which is minus 90 degrees and plus 90 degrees in phase. And you can send 2 bits instead of 1 bit. So instead of having a splodge here, 0, and splodge here, a 1, you can have splodges at different phase angles. And if you have 4 splodges, you define them with 2 bits of data. So you double the data rate using that modulation formula. Is that clear enough? This is it's sort of art, really, rather than science. But what I've done here is I've turned up the coefficient on the nonlinearity compensator. So I've turned up the effective length in my compensation equation. And it's saying one of these subcarriers in the OFDM system would have been out here if I hadn't compensated it. But as I turn up the phase modulation, it comes back and tightens up the cluster. And there will be some below the axis, like this black one here, which would have been an error. So instead of being in this quadrant and being detected as 0, 0, it would have been detected down here as a 1, 1. If I turn the compensation on, it comes back into the nest, if you like, and the error rate goes down. We can also do things like, this is the effective compensation length per span. So I'm just turning up the gain on this equation. And I find that at a certain effective length, which tends to be about half of the effective length, I get a peaking in Q. Q being the signal quality. So I'm trying to get towards this maximum. Now, that is essentially what I did. If you want to do it in optics, this is the way to do it, rather than digital. So you basically take the output of your transmitter, you detect it with a photodiode that detects the intensity, you multiply the intensity by the number of spans, the nonlinearity coefficient, and gamma. Gamma is the nonlinearity coefficient, and this effective length, which is a tuning parameter. And then you use a phase modulator, like a lithium niobate phase modulator, and that applies the phase shift. So that is nonlinearity compensation. The problem is that walk-off makes this work less well, because it's applying a phase shift based on the waveform out of the transmitter, but as the waveform goes to the fiber, because of dispersion, it evolves, changes shape. And therefore, at the receiver, it might be completely different to being at the transmitter. So if you apply this compensation phase, it won't be right for compensating the four-way mixing at the receiver. A slight modification is to put one of these at the receiver. A better modification is to put one of these every so often. That would work well, but maybe you don't want that complexity along the link. We find, though, that if we put a low-pass filter, which is an electronic filter, a resistor and a capacitor, costing 10 cents, then we can make this system work a lot better. And the reason for that, I hope I've to go back to this one. The reason for that is this graph. That if we have a broadband photodiode and a broadband phase modulator, then it's trying to compensate for these high frequencies. But the high frequencies don't matter because of walk-off. They're cancelled in the actual fiber. So if you try and compensate them, you're compensating for something that's not there, which is worse than doing nothing. So if we limit the bandwidth of our compensation to only low frequencies, then we're compensating for this main lobe, I suppose, in the response, where all the damage is done. But we're not compensating for this bit because walk-off has already reduced the effect. And so a low-pass filter, a very cheap electronic circuit, will improve the system. And actually, it's even better than that you can use a photodiode rated at 2 gigahertz rather than a photodiode rated at 40 gigahertz. And they're far, 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 far cheaper. And you can use a phase modulator rated at 2 gigahertz rather than one rated at 40 gigahertz. And so using cheaper components actually works better. And I think that the first law of physics to me is if you want something to work better, you should spend more money. You never get anything for nothing sort of thing. There's no such thing as a free lunch. Well, this breaks that fundamental law of physics of something for nothing. So I think it's rather good. Now, just to show that the filter passband matters, we've got two systems here. One is fully periodically dispersion compensated. That basically means you've got a dispersion compensation every 80 kilometers. Don't like that anyway because it has the full bandwidth of nonlinearity. The walk-off no longer happens. This is a green field, well, it's almost green field. It's got a bit of residual dispersion per span, so the dispersion sort of goes up, down a bit, up, down a bit. This is a bit like real big communications companies suggest. And what it's saying is, if you optimize this filter, obviously if you put a zero bandwidth filter, then you're not doing anything at all, so it doesn't work. But if you choose a filter with a bandwidth of 2.5 gigahertz, which is quite small in today's technology, quite low cost, then you can get a Q improvement of 2.8 dB. What does that do? Probably gives you about 40% more data capacity down the link, which is not bad for a few $100. But what about cross-phase modulation? Cross-phase modulation is thought of as the ultimate limit to systems capacity. This is one dog affecting another dog, or one WDM channel affecting a neighboring channel. And the pain about this is that you could compensate it digitally, but you would have to have knowledge of all the channels. So essentially you could do a systems simulation called a technique called backpropagation, where you take the output of your receiver with all the channels over hundreds and hundreds of gigahertz, you digitize it, which is almost impossible until Arne and I create an analog to digital converter that works at such speeds using nonlinear optical components. You could digitize the whole damn thing, and then you could do a split-step Fourier method computation and undo all the XPM. But that's sort of impossible at the moment. It would require huge amounts of computation because of the bandwidth. But we've just shown that the bandwidth doesn't really matter. A small bandwidth works quite well. So can we use what we've learned in the previous slide to compensate for XPM? So back to this one. What this says is, actually, in my four-way mixing graph, the efficiency graph, there's a product, a geometric mean, of this delta F and this delta F. So if you have one channel affecting another channel, that means this delta F is big, like 50 gigahertz or a multiple of it. And that means that this one has to be small to get any four-way mixing efficiency at all. So only close frequency components in the first dog, the aggressive dog, are affecting the second dog, if you like. So the beat, only low frequency beats between these components in the first channel will affect distant channels. And what that's saying basically is only low frequency intensity fluctuations that you could detect with a low frequency photodiode here will affect another channel. So cross-phase modulation is limited in bandwidth. And this means we can compensate it. And this is rather complex, but the guts of it are here. So I've got my same system where I've got a photodiode, an amplifier, a low-pass filter, and a phase modulator. The trick, and it's quite a simple trick, but I believe it is an inventive step, is that rather than putting this stuff, compensator, after the demux, so it only operates on one channel at a time. You put it before the demultiplexer. So all the WDM channels, each one of them is going up and down, forming an intensity fluctuation, and you just sum them all with photodiode and modulate the phase in proportion to the sum of all the intensity fluctuations, which is magically done with a very low-cost photodiode. And that's how you compensate XPM. So does it work? Well, this is sort of slightly difficult to understand, but if you've got no compensation, the quality of the channel is these orange dots, oranges, I suppose. And the middle WDM channels are affected more than the edge ones. It's because they've got more neighbours close to them. So this is very bad because all the neighbouring channels are affecting its quality through cross-phase modulation. The edge channels don't have any neighbours here, so this one is affected by that, for example. If we compensate for XPM by detecting all the channels and applying a phase modulation, we get these triangles, little trees, green Christmas trees, let's say. Because these are affected by XPM, we can get quite a good increase of about 1.5 dB using the technique. For the middle channels, the edge channels are not improved that much because they're mainly affected by self-phase modulation by themselves. But we can also apply self-phase modulation compensation either digitally or using the same technique after the demultiplexer, and that will take the green Christmas tree up to the red Christmas present here, and we can improve the channel above the magic number of 9.3 dB, which is a system with a bit error rate of about 2 times 10 to the minus 3, which is the limit that people will accept. If we apply both, which are these blue balloons up here, then we can take every channel up beyond the FEC limit. And therefore, we've made every channel of this system go from potentially a very low quality factor to a quality factor that after FEC will give us error-free compensation. And that's how to compensate for XPM using very simple components. Any questions? Now, it's not getting rid of it entirely because of walk-off effects, but you could apply this at many places along the link and you would get a better compensation. But the beauty of it is that it uses low-cost components working in gigahertz bandwidths to do something which is over many channels, so many hundreds of gigahertz.
How long is it? Do the lengths have to be the same? Do you have to synchronize the lengths?
Yes, this path and this path must be synchronized, otherwise you're applying a waveform out of phase, or in phase actually, and so you would actually make the situation worse. So we're going to try and build this, and it will require some careful tuning to get it right, which basically means putting some fibre around drain pipes, stretching them apart to make a variable fibre optic delay line. But you could automate that and you could manufacture it, put in microwave phase shifters if you wanted, or perhaps, as I say, just to find a stretcher to make it work. I guess this brings another idea, which is what we used to do at Melbourne Uni, where we had electronics which was slow, i.e. it took some time to get through, and fibre, which is fast, and you just make this fibre longer and put a delay on it. So by the time this has gone through all these electronic components, they've reached the phase modulator at the same point.
So are you saying that it applies to any with or without DCF you should be able to get improvements?
This one will actually work better with DCF because DCF prevents walk-off. So it means that four-way mixing and crossfade modulation are really bad. But it also means that the waveform along the link, particularly at the beginning of each fibre span, is identical. And therefore, at the last fibre span, if you know the waveform, you know the waveform in all the previous fibre spans. So we can compensate for the whole lot with one compensator. So if you design a very bad link using dispersion compensated fibre, where there's very strong XPM, then this will get rid of it. If you get rid of the DCF along the link, the four-way mixing and crossphase modulation will go down in intensity. But it also means that the waveform evolves along the link, and therefore it's difficult to look at one point along the link and predict how much phase you should apply.
So do you think you need to go back to fully compensated links every time, or does that need to be investigated?
Which is best, you mean?
Yeah.
There may be a sweet spot where you have residual compensation, which means if you look at the dispersion along the link, you tend to start like that. I wish someone would invent a pen that worked. That would be real. So the dispersion, you start off negative, you go up, you go down, you go up, go down, you go up, go down, and that sort of thing. So each span has some uncompensated dispersion. That's the dispersion compensation module. That's sort of DL. And that's typically used in many communication systems, long haul ones. People spend a lot of time trying to optimize that sort of pattern. What I'm saying is basically start at zero and just go up. Don't compensate it. The worst situation is where you compensate it exactly every link. And that means the four-way mixing or crossphase modulation generated at the start of each fibre span is in phase. And all these from things are like that in all together. So, how long have I got? I guess you want to know where the room for optics is. So what's the problems with this? Well, the analog to digital converters, the current state of the art is 56 gigahertz samples a second, which, if you use IQ modulation, gives you a sort of bandwidth, an optical bandwidth that you can down convert of around 56 gigahertz. Their analog bandwidth is a bit less than that, but you can buy the front-end analog to digital converters to do 100 gigabits per second links. And you can enter various deals with various manufacturers to do various customizations of that. But if you want to go at higher data rates, you need faster analog to digital converters. And the hard thing there is fast sampling and fast low jitter sampling, which is why we need mobile lasers. Other things, well, this is a poor man's mid-span spectral inversion. So ultimately, if you put a phase conjugator in the middle of the link and make all the blues reds and the reds blues, then you can actually use the fibre itself to compensate for the whole of XPM and four-way mixing. The issue there is always finding the middle of the link. One solution is perhaps to do mid-span spectral inversion at the end of the link, which I believe has been done here. Fourier transforms. We believe it's possible to do Fourier transforms that are fast enough to do OFDM in silicon, even non-custom silicon. So these are really, 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 really fast, running on tens of billions of points per second. However, there may be some advantage of doing Fourier transforms optically. And indeed, this demux is often designed to be discrete channels. So you put in a signal, it splits it between discrete channels. If you replace that with an optical Fourier transform, you'll get the ability to pack the channels closer together. So redesigning that optical filter is an interesting thing. And to make a proper Fourier transform, it ought to be a filter followed by fast optical sampling. So optical sampling might be useful after that component. So I believe there's room for optics, for doing very, very fast things. But there's also room for actually quite slow electronics to do reasonably clever things. And it's all based on that four-wave mixing efficiency curve, which I guess comes back to these fronds. That's the sort of key diagram, that if you look at four-wave mixing and how it accumulates along the fibre and treat it as little vectors, just summing up and changing phase every step, click, 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 then you can get an idea of how certain frequency components build up in a link and eventually add in phase, or if you're lucky at some frequencies, cancel one another out. I hope that's really interesting. Any other questions? Yes?
Your nonlinear efficiency curve, I think about 3 slides forward, are there issues?
Yeah.
What are the resonances there? So I can understand the DC part. Why does it come back up again?
Yeah. These nulls are where, I believe the nulls are where you've got multiple spans, and each sort of, the resultant of each span comes back on itself. So there's various situations that this can occur. Say I've got 10 spans, each one produces a four-way mixing like this. Really, that's a little frond that comes around. I can't bother to draw that. So each one produces its little frond, like that, and then, oh, this is 8 spans. You see how many spans it is? It comes back to the origin, and that produces a null. So the four-way mixing at that particular frequency over that number of spans does that. Now, of course, there's a situation where you can go around twice with 8 spans and get back to the origin. So that produces a null. And that's occurring at twice the frequency separation. So this is probably where it goes around once, this is where it goes around 2 times, this goes around 3 times, etc., etc.
The peak, though, what's called
The second peak, that's where it goes round, it goes round a number of times, but, let me draw this. So it goes around a number of times, but it ends up away from the origin. So it's going round not a huge number of times. So it's lower because it's the first 4 have cancelled out, the second 4 have cancelled out, but the last one hasn't. And that produces this second peak. And the general decay is the frondiness, that the higher the frequency separation, the more folded up it is. Now this 3 groups in 1990 came up with the same thing. One was Andy Ellis at British Telecom, one was a guy called T.K. Chan, I believe, at AT&T, and then there was a guy at NTT as well. And so it's sort of nothing new. It was when they first came out, Simon Poole's law, optical amplifier. Oh, we'll make a link with lots of optical amplifiers. Oh, we get four-way mixing every so often, strongly, because the power's strong here, here, and here, here. Oh, how does that add? Does it add in phase or anti-phase? And they all came up with that correct. And it's 20 years old, so nothing new under the sun. The question is, how do you use that information? thank you very much for coming after the Thursday night out.
Everyone, let's thank our third again. Probably have a bit of a break. Just one quick announcement. We have a